as it is throughout your reaction. And if you got primary radical at the propagation stage, you will get the primary radical throughout your reaction. It won't getting changed, it won't achieve the higher stability by shifting the free radical. So it's not possible in case of free radical. Okay, next one. Now we will go for some, that means energy calculation, how much energy we need for primary radical, primary isopropane radical, primary or secondary radical, and how much energy we needed. Okay, so here in this slide, chlorination to give chloropropene. Okay, secondary radical generated over here. Second radical, okay, chlorine radical, that one is generating secondary these alkyl compound free radical, and the remaining chlorine dot, that one is getting reacted with H dot, whatever, that one is homolytically detached from the your isopropane, N propane, sorry, not isopropane, it's N propane. Okay, so bond form, HCl bond has been formed. So energy needed to form HCl bond, it's 103 kilocalorie per mole. Bond to break CH bond, energy needed 98 kilocalorie per mole. Okay, for chlorination. Next, to form radical, that means to form sigma bond in between chlorine radical and your that means N propane radical. So formation of CCl bond, energy needed 83 kilocalorie per mole, and to break CSCl bond is 58 kilocalorie per mole. So see, energy calculation shows that why we do get chlorine as a radical very quickly, because this chlorine bond is very weak and we can cleave it very easily, because it needs less energy, 58 kilocalorie per mole. So in that way, bonds broken, for breaking bonds, CH bond and ClCl bond, total energy consumed by that molecule is 156 kilocalorie per mole, and total energy needed to form bond, it's 186 kilocalorie per mole. So in case of chlorination, formation of bond, it needs extra energy 186 kilocalorie, and formation breaking of bond, it needs less energy 156 kilocalorie per mole. Okay, and next, in another case, for primary halide formation, that means to generate primary radical, primary radical, or to generate that thing, we need whatever energy calculation is the same one. Bond form, whatever bond form for the secondary radical and whatever bond form for the primary radical is the same, 186 kilocalorie per mole, 186 kilocalorie per mole. And you if you will pay attention, formation of, that means bond broken, whatever bonds has been broken, CH bond or chlorine bond, so those bonds has broken, it needed, in case of primary free radical, the energy needed to break that bond, it's higher than the secondary free radical. So it's a 159 kilocalorie per mole for the primary alkyl halide. So you can see in, so if we will compare the energy needed to break the bond, it's less for primary free radical, it's less for secondary free radical, and it's higher for primary free radical. So obviously, if you need less energy, this reaction will prefer over the primary free radical. Okay, so now we will go for the bromination. Okay, so bromination reaction, we have to count for the energy. So as up to now we have seen, bromination reaction is more selective for the secondary halide formation, is more selective for compared to the chlorination. So here we will see now comparison of the primary bromide formation and secondary bromide formation. So if you as usual, initiation stage, then propagation stage, and lastly termination stage, everywhere you will find the same stages. So now in initial Br dot, we got Br dot from Br2 by breaking Br bond. So to break Br bond, we need energy, total energy 46 kilocalorie per mole. It's relatively less than the chlorine bond breaking. Okay, so for to cleave chlorine bond homolytically, we need 58 kilocalorie per mole, and to cleave Br bond homolytically, we need 46 kilocalorie per mole. This is the one point which supports the formation, that means selectivity of bromination, of secondary bromide formation. Okay, so this is the reason. This is first reason that why bromination is more selective in case of isopropane. That means secondary bromo compound we can get selectively because we need less energy to cleave the BR-BR bond. Okay. Next, bromination in case of prime formation of primary alkyl halide. Okay. So in case of primary alkyl halide, we have to generate primary free radical. Okay, so to generate primary free radical, the same energy needed to break BR-BR bond 147 kilocalorie per mole. So here is the and then the formation of CH, that means bond breaking primary halide, that means primary to generate primary radical, the to break the CH bond from the terminal methyl group, the energy needed to break that CH bond is higher, 101 kilocalorie per mole, and due to that the halogenation primary halogenation reaction is less selective, and it's so more selective than the secondary radical, secondary alkyl halide formation. So here is the reason why secondary alkyl halide is formed selectively over the primary alkyl halide. Next one. Okay, so we will go for the next. So everything is depend upon the physical thing. Okay, the physical chemistry relays behind this one, so we don't need to go too much detailed thing about the this thing, what is the things relates based on this one. Okay, so some point we will cover here. You if you will imagine that activation energy, that means we know each and every reaction it has its own activation energy, and all these things it would can explain on the basis of the Arrhenius equation. Okay, so some basic thing you should have know, that means you should be familiar with that one. That's why I have added this slide. So this is the Arrhenius equation, and on the basis of this Arrhenius equation, we can define why the bromine is more selective than the why bromination is more selective than the chlorination. Next slide. Heat increases. Okay, it increases the average velocity and energy of molecules. Okay, so this is also one of the basic thing. It relates to velocity of molecule and all. So not we cannot no need to go for too much detail. I will provide you the PowerPoint, so you can refer that things. Next one. Next slide. So still the question is unanswered. What does that have to do with the selectivity of hydrogenation? That means the energy of activation energy, and we will see the how the energy of activation plays part in the halogenation reaction. Okay, so reaction mixture is heated. Okay, after heating is very common that we do heat the reaction mixture, and a lot of things depend upon the how much energy you have to provide to the uh, reaction and all. Okay, so the reaction mixture is a larger proportion of the molecule will have sufficient activation energy EA to react. Okay, so reaction with activation energy EA at very cold temperature, very few molecules have sufficient energy to react. Okay, so at low temperature, as we increase the temperature, as we heat the mixture, the proportion of these molecules increases, and that's why the rate of reaction also increases as we increase the heat. Here is an example how it works. Note how in this case in graph you can observe at 300 Kelvin the reaction doesn't occur. Okay, 300 Kelvin reaction doesn't occur, but at 330 Kelvin K reaction starts to occur at reasonable rate. Okay, now the thing is how the energy of activation work with the selectivity of bromination reaction. We will see. We will check out for the answer of this thing.